Hi and welcome to this lesson that will be about 16.2 activation energy. Before we start the lesson, I would like you to bring your GDC, your calculator. You will need this. And also you need your chemistry data booklet, this one here. So let's get started. 16.2 activation energy. We're going to start with the syllabus and the essential ID. The essential ID says, for this topic, says that the activation energy of a reaction can be determined from the effect of temperature on reaction rates. So we are going to connect what we already know from 16.1, reaction rate, with some calculations. We are going to use Arrhenius equation today. Yeah. So the understanding in syllabus says that the Arrhenius equation uses the temperature dependence of the rate constant to determine the activation energy. So we're going to look at this mathematically and how we can determine rate of reaction of the rate constant or the activation energy. And we're going to do it with the help of the Arrhenius equation. Yes, we're going to start now with Arrhenius equation. Please bring your chemistry data booklet, section number 1. You have it here. And we are going to section number 1. Here. And you can see here and here we have two different here I would like you to look at. This is the Arrhenius equation here. And you also have it in logarithm, as ln, here. So we're going to use these two here. The thing is that the rate constant, as we have determined before, is temperature dependent. So what happens if the temperature increases? Well, we could sketch maybe a Maxwell-Boltzmann diagram here, like this. Something like this. We have the number of particles here, and we have the ng on this axis. So this is the distribution diagram. What happens if the temperature increases? We can say that this maybe is the EA, activation energy. It means that all the particles that are here have enough energy to react, collide. If we increase the temperature, we can see in the diagram that the peak will be like pushed, something like this and this. So if this was the normal temperature, T, the T temperature plus the increase in temperature, we say that more particles have enough energy to react. And we know that because if we put in heat, more particles will move more and they will collide more, and it is in the collision we know the reaction occur. So the frequency of the collision will increase. And the rate constant for the rate or the reaction is temperature independent, because if the temperature increase, more energy for more particles to collide. One thing is that actually understand it, but we also need to do maybe some calculations on this. And we're using the Arrhenius equation. Arrhenius equation says that the rate constant K is equal to IE up to minus EA divided by RT. The K is the rate constant, okay? So K is the rate constant. This one here is the activation energy. No, frequency factor, I'm sorry. And the EA is the activation energy. R is the gas constant. You have that in your chemistry data booklet, section number 2. I'll show you. So you have the R constant here. This is the number you should use, 8.31. And the last thing we have in the equation is T, stands for temperature. And really important here is that this should be in Kelvin degrees, so don't forget that. Okay, this is one version you can use, but we also use the logarithmic form. And what we do is, you can look in your chemistry data booklet again, section number 1. You have it there in section number 1. Just to remind you here, I will write it for you. You take ln for K, the rate constant, is equal to minus the activation energy divided by the gas constant times the temperature plus the ln for the frequency factor. So this is the equation you need. You need to now understand how to use it. So this is the next thing I'm going to show you. If you're looking at it, applications and understandings in your syllabus, they say that I'm going to use this now. So, Arrhenius equation. So, the understanding of the equation. One other thing you have to have in mind is that the Arrhenius equation is an example of an empirical relationship, as it cannot be proven mathematically. Okay? And the expression of E up to minus EA divided by RT is known as the exponential factor and represents the fraction of the reactant particles that has sufficient energy to react. This is what I showed in the Maxwell-Boltzmann diagram. And the A is the frequency factor, is the constant, and relates both to the frequency of the collisions and to the steric factor, which is fraction of the collisions between the reactant species that have the correct orientation to react. So we need to know the frequency factor. And one thing more, note that the E up to minus EA divided by RT is dimensionless. Okay, enough with this. I'm going to show you some calculations. Okay, this we actually did together in lab before you went home. We look at what happened if we increased the temperature for a reaction. When we did it, we actually increased it by 10 degrees. And a rule of thumb is that if you increase the temperature with 10 degrees Celsius, you can expect a double rate of reaction. It means that it will go double as quick. You saw it when we did, remember, the cross, like this, and we have the beaker on. And we measured the time it takes for the sodium thiosulfate to react with hydrochloric acid. And we saw that if we increase the temperature with 10 degrees, around double as quick. It takes half of the time to make the cross disappear, or but not be seen through the beaker. There are some different things here we need to have in mind. One of the things is that it's only true when the activation energy is about 50 kilojoule per mole. If we have another activation energy, this will not do, okay? Since concentration is constant and temperature is altered, the rate is directly proportional to the rate constant. And now I'm going to show you how we can do if we want to compare the rate at 298 Kelvin degrees compared to 308 Kelvin degrees. Note that I have increased it here by 10 degrees. And we're going to use the Arrhenius equation to compare the rate. Okay, we can start with if we have 298 degrees of Kelvin. We also expect it to be 50 kilojoule per mole. When you do this, you can convert it to joule only. Also, maybe I need to write the equation here for you so you have it in front of you. K is the frequency factor, and then we have this one, EA divided by RT. So the EA is 50,000 joule per mole. R is the rate constant here. Look in your chemistry data booklet, 8.31. Joule per Kelvin per mole. And this is why I changed this from kilojoule to joule, because we have joule only in the gas constant. We need to have the same prefix here. That's why I have chosen to do like this here. And the T, the temperature, in this case we're going to examine what happens if we have 298 degrees of Kelvin. We don't know the frequency factor, but we can still examine what will happen, okay? So, just gonna put this away. K is A, and then we have this one up to minus 50,000 divided by 8.31 times 298. Take your calculator. I don't know if you see it. See here. Yes, okay. So what I did to make it really simple and easier to do it on a calculator is that I take minus 50,000. This is this one here. See, you have minus here also. Forgot it here. Need a minus sign here. Okay, so minus 50,000 here is the activation energy. I take this with parentheses around it. And then we take 8.31 times 298 and we divide this, and then you take E up to and this answer here to get 1.7 times 10 up to minus 9. A, we have this A left here, okay? Then we do the same thing for 308 degrees of Kelvin. So this was the rate constant at 298 Kelvin degrees. Now I want you to click the pause button here and try to do the same thing if you have 308 Kelvin degrees. So click pause and I will show you how to do it later. Okay, so instead of having 298 as we had here, we get instead examine what happened is 308. If you push this in your calculator, please do it. And you see that this will have 3.28 times 10 up to minus 9 A. And you can see that it's almost a double here. So we can see that the rate constant will be doubled if we increase it by 10 degrees. Okay, now I want you to try on your own this assignment, so read it carefully, look at the information I have given you, and then try to compare what will happen with the rate if the activation energy EA is 100 kilojoule per mole. And then I want you to compare it from 298 to 308, okay? Now again, click the pause button and try on your own before I will give you the answer. Okay, this one here is important. We're going to examine what happened if we have 298 compared to if we have 308 Celsius Kelvin degrees. The activation energy EA is 100 kilojoule per mole, so it's 100,000 joule per mole, like this. And the Arrhenius equation here. The activation energy is this one here. R we know, the gas constant 8.31 joule per Kelvin per mole, like this. And the T for the first example will be 298, and for the other example you will examine 308, okay? Okay, so if you put in the correct numbers now in the equation, you can see that we will compare it from 298 to 308. Frequency factor is unknown, you can just let it stay as it is. And then we have E up to minus 100,000 divided by 8.31 times 298. If you want to examine a temperature of 298 Kelvin degrees. We compare it with what happens at 308 Kelvin degrees. Here is the frequency factor, E up to minus 100,000 divided by 8.31, the gas constant, times the temperature 308. If you put this in your calculator, I will give you a minute just to try on your own. give you here. Can you see it? Almost right. Be really thorough with the parentheses here. It's important, otherwise you will end up wrong. So minus 100,000 parentheses here, divided by the gas constant times the temperature here. Around minus 40 should be correct, and then you take E is the blue thing here, so you need to activate the blue thing. I take second and up to, and then you take the second ans here to get the answer inside here, and you will get the correct answer here. (2.90 times 10 up to minus 18 A. If you do the same thing now for 308, try on your own on the calculator. Once again, be aware of the parentheses here. Minus 100,000 here, 8.31, 308, parentheses, 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 and then I take E up to, and then this one here. So you will get the answer to 1.07 times 10 up to minus 17. And if we just compare this to, we want to know how many times this will fit in this number, and we do that by dividing that one with this one, and we'll get the factor to 4. It means that we cannot see the double. Even if we increase it by 10 degrees, it's not a double, it's 4 times more, and that is because we have another activation energy. We don't have. The rule of thumb was that we should have 50 kilojoule per mole, but now we have 100. That's why the factor should be 4 instead. Now I'm going to show you how we can use the log version of the Arrhenius equation. We want to determine the values of EA and A for a reaction, and that is if we have the value of K is known for 2 different temperatures. We have the T1 and T2. Then we can use another version here. The value of activation energy can be determined by solving simultaneously equations, and we use the log version of Arrhenius equation. Please look at your chemistry data booklet section 1 to find the Arrhenius equation. When the activation energy has been calculated, you could then use Arrhenius equation to determine the frequency factor. So that is what we're going to do now. So this is the assignment. We want to determine the values for the rate constant of a second order reaction at 25 Celsius degrees and 37 Celsius degrees. We can see that the rate constant is for 25 degrees, 4.26 times 10 up to 3. So this number is to 25, and this number here is to 37, okay? That's why it's called respectively 2, so you can match it. We want to deduce these 3 things. We want to deduce the activation energy, the frequency factor, and the rate constant later at if we have 50 degrees instead. We want to use 2 significant figures also. So please now push the pause button, try to figure out some of the things by your own, and I will show you. Okay, we will start by looking at the activation energy. I will give you a blank paper here so we can look at this. So A, activation energy. How do we do to determine the activation energy? What you will do is that you will use this equation here in the chemistry data booklet, this one here. And this is because we have two different temperatures, so that's why you use this one here. I will write it up here in the paper also. We have ln K is equal to the minus of activation energy divided by gas constant times the temperature plus the ln for the frequency factor. And then we can use or isolate this here. ln, we have the two different temperatures. ln K1 divided by K2, EA divided by R divided by 1 T2 minus 1 T1. First temperature, second temperature, okay? So the K1 and the K2 will match with T1 and T2, okay? So if T1 is the first temperature, then the K1 is the first rate constant. So you need to match it from the information you get in this one here. So I can put it here maybe. So if we have temperature of 25 degrees, be aware that we want to have it in Kelvin degrees, so you need to add 273. So the Kelvin degrees is 298. And the second was 37 degrees plus 273 to convert it into Kelvin, so it's 310. The first rate constant for 25 was 4.26 times 10 up to 3 mole cubic decimeter S up to -1 here. And then the second one for T2 here was 1.82 times 10 up to 4 mole cubic decimeter S up to -1. Then we want to put this in the equation here, the numbers we have. K1 was 4.26 and K2 is 1.82. EA we don't know, but we know the gas constant, 8.31. And then 1 divided by the second here, 310, minus 1 divided by 298 here. If you solve this, I have actually done it here, so I can just show you. You see that we have put in the here. And first I just work with this one here, work it out here. And then this times this is up to this one here. And then you want to solve EA on one side. So in the end you will get around 93 kilojoule per mole, okay? So if you are not ready here, you can just click the pause button so you can look at it, okay? The next question was that find the frequency factor. Use the Arrhenius equation. You know now the activation energy. And they want you to know the frequency factor. We can use the first one. Either way, you would use it when you have temperature 1 or 2. So K1 and T1, or K2 or T2. I will use K1, T1. Okay. Once again, Arrhenius equation. Rate constant is the frequency factor, E up to minus EA divided by RT. So we have K1 here, 4.26 times 10 up to 3. We don't know the frequency factor, that's what we want to calculate. E up to minus EA we have determined now, 93 is the activation energy. And is, yeah, kilojoules, so you need to convert it to just joules, so it's 93,000 joule to 3 divided by R, 8.31 times the temperature, and that is 298. Solve out A. The A will be 8.7 times 10 up to 19, and the unit will be the same as the rate constant, mol dm3 s up to -1. Okay. The next thing we're going to look at is the rate constant at 50 degrees. Last thing today. So the temperature is 50 degrees plus 273. So you need to add this one with this one. So it's 323. Once again, the Arrhenius equation is K and frequency factor E up to minus EA divided by R times T. You know now the activation energy, you know the frequency factor, but you want to determine the rate constant if we have another temperature. So T is known, R is known because it's a constant, 8.31. EA is 93,000 joule. Yes, and we know the frequency factor also now, 8.7 times 10 up to 19 here. Just put in the numbers in the equation. K 8.7 times 10 up to 19, E up to minus 93,000 divided by 8.31 times the temperature, 323. That will give us rate constant to 7.8 times 10 up to 4, and again same unit as always here. Okay, I hope this gets a little bit more clear, that you have some help from the video. Thank you.